So, welcome to lecture number 4 on DC theory part 3 as we look at delta star transformation. My name is Charles Golia. So this lecture will cover the syllabus components of network simplification using star delta transformation or delta star transformation. And the presentation outline for today will cover delta star or delta Y transformation in detail, and the star or Y to delta transformation. And then we'll look at some of the examples and I'll give a tutorial at the end. So, star delta transformation is best used in situations where resistors are neither connected in a pure parallel circuit or pure series circuit, but you have resistors in between, and they are such that you can't easily simplify them or analyze them. Therefore, we employ a method of delta star or star delta transformation to help us in finding the equivalent circuit. And so, depending on the nature of the circuit, you choose whether to break it into or transform it from delta to star or star to delta. Let's begin by looking at delta to star conversion, transformation. So in delta to star conversion, this one is achieved using 3 equations, equation 1, 2, and 3 as given on this slide. And let's assume here we have a circuit as given in figure 1. And this circuit is such that it has got 3 resistors connected in delta, RA, RB, and RC. These are all connected in delta, as you can see going by the outer circuit here. And now, if we are to transform this circuit to the star equivalent, which is a circuit given as R1, R2, and R3, the inner circuit here, going by the rules of delta to star transformation, you simply, if you want to calculate R1, you get the resistors that are adjacent to R1, in this case RB and RC, multiply them, divided by the sum of all the resistors that are in delta, in this case RA, RB, and RC, as shown in equation 1. Equally, to calculate R2, you get the adjacent resistors, to the adjacent resistors to R2, in this case is RA and RC, multiply them, divided by the sum of all the resistors connected in delta. In this case, again, RA plus RB, and include also RC, as shown in equation 2. And then to calculate R3, you get again the adjacent resistors here. This is RA and RB. Multiply them, divided by the sum of all the resistors connected in delta, as shown in equation 3. So having understood these 3 equations, let's try now and do an example, simple example where we convert from delta to star, but now using actual values. If you look at figure 2A of example number 1, you have 3 resistors, RA, RB, and RC. RA, RB, and RC, they are connected in delta. Then now we need to transform this circuit into the star equivalent. So to convert this, what you do is you calculate R1, and in calculating R1, you get the adjacent resistors. R1 is somewhere here. So the adjacent resistors are these 2 here, RB and RC, which is 10 times 25 divided by the sum of all the resistors connected in delta. In this case, it's 15 plus 10 plus 25, which gives you 50. And so 50 into 250, you get your 5, which is your R1. To calculate your R2 again, you get R2 will be somewhere here. So the adjacent resistors will be RA and RC. So which is 25 multiplied by 15 divided by the sum of all the resistors connected in delta, which is 15 plus 10 plus 25, and you get the final answer as 7.5, which is your R2. And finally, to calculate your R3 will be somewhere here, so which is basically that one there. What you do again, get the adjacent resistors RB and RA, multiply them. In this case, it will be 10 and 15, get 150 divided by their sum, which is 15 plus 10 plus 25, which is 50. 50 into 150, you get your 3 ohm resistor as your R3. So again, in the next slide, what I've done is essentially to connect, to show the calculations of these 3 resistors, R1, R2, and R3, to arrive at 5 ohm for R1 and 7.5 for R2 and 3 ohm for R3. Next, I want us now to discuss the conversion from star to delta. Suppose now you are given the values of R1, R2, and R3, which is a star circuit shown in the inner circuit here. And you want to convert this star circuit to the delta circuit, which is shown on the outer part of that circuit, to calculate RA, RB, and RC. So to calculate RA, what you do is RA is here. Okay, your RA is essentially here. Multiply R1 and R2 plus R2 and R3, which is that part, plus R3 multiplied by R1. So you go around multiplying each of these in pairs of 2, R1 multiplied by R2 plus R2 multiplied by R3 plus R3 multiplied by R1 in that fashion. So you go around like that, then divide everything, but by the resistor opposite to RA. In this case, it is R1. So make sure that here you, after you've done the multiplication of R1 plus multiplied by R2 plus R2 multiplied by R3 plus R3 multiplied by R1 plus, then you divide by the resistor opposite to R1, RA, which in this case is R1. Therefore, you have your equation 4 for calculating RA. To calculate RB, which is here, your RB, again, it will be R1 multiplied by R2 plus R2 multiplied by R3 plus R3 multiplied by R1, divide by the resistor opposite to RB, in this case is R2, and that's how you get your equation 5. Finally, to calculate RC, which is that one, again, it is R1 multiplied by R2 plus R2 multiplied by R3, you go around, plus R3 multiplied by R1, divided by the resistor opposite to RC, which in this case is R3, and then you arrive at equation 6. Now, situations may arise where the resistors connected in delta may be the same. So RA, RB, and RC are the same. They have the same value. The question is, how do you convert them to the star equivalent? So for same values of resistors in delta, let's assume this is 9, 9, 9. How do we easily convert this circuit to an equivalent star of R1, R2, and R3? So to do this, you employ the first part of the equation. So to convert to star, all you need to do is pick one of the resistors connected in delta, which are the same, whether RA, RB, or RC, divided it by 3. So in this case, to calculate R1, which will be the same as R2 in star, which is the same as R3, just pick any one of the resistors in delta, 9 divided by 3. So you get 3 as the resistor for R1, R2, and R3. Equally, you can do the same, assuming you have a star circuit and the resistors in that star are all the same. Let's assume it's 3. Then you want to take it to equivalent delta. So what you do is, for RA, RB, and RC, okay, so in this case, to calculate RA, which will be the same as RB, the same as RC, the equation you're going to use is the second part. It will be simply 3 multiplied by n of the resistors in star. That is your 3. You'll finally get your 9. So having understood this, let's now do a practical question where you have resistors connected in parallel, some in delta and some in star. How do you reduce it? Or come up with equivalent resistance and calculate any other parameter such as current or voltage, depending on the nature of the question. So in figure 4, you have a 30 ohm resistor connected between terminal A and B, so it's in parallel. But in between there, you have 3 resistors connected in star. If you want, again, I can see a delta connection of these 3 resistors. And I can also see a delta connection here between these 2 resistors. So you can choose which pair to begin by breaking, either into either delta to star or star to delta, as you simplify this circuit. For me, let me choose to start by turning this into a delta, a star into a delta, this circuit into a delta like that. And then the idea here is, let me find RA, let me find RB, and let me find RC. So to find RA, that is, you're converting from star to delta. So it will be the resistors in star, 5 times 10, 5 times 10, plus 10 times 20, plus 20 times 5. Everything divided by the resistor opposed to RA, which is 20. Find RB, it will be, again, 5. The numerator will remain the same, times 10 multiplied by 20 plus 20 multiplied by 5, everything divided by 5. Then RC, you're going to get RC, the numerator remains the same, 5 times 10, 5 times 10, plus 10 times 20, plus 20 times 5 divided by 10. So when you do that, you end up having a scenario as shown here, with your RA being equal to 35, your RB be equal to 17.5, your RC be equal to 70. And once you've calculated your RA, once you've calculated your RA, RB, RC, this can now be redrawn. Your circuit can now be redrawn to look like this. So you redraw the circuit and you discover that your star point which you had, your star circuit which you had around here has been reduced to the equivalent delta. Now the circuit can easily be simplified because you can see here that 70 is in parallel with the 30. The 12.5 is in parallel with the 17.5. The 15 is also in parallel with 35. The answer you get here, let's call it X, and the answer you get here, let's call it Y, which is your X is what you are getting when you parallel these two, and your Y is what you get when you parallel the 15 and the 35. You notice that then finally X will be in series with Y, but in parallel with the 30 here. Then you'll have gotten your equivalent resistor, which is the resistor between terminal A and B. That's your overall equivalent resistor. So what I've done here is, in my next slide, is to show those details. You can see that the 70 will be in parallel with the 30 to get 21. The 12.5 is in parallel with the 17.5 to get 7.292 ohm. 15 and 35 are in parallel to get the 10.5. Thus, the equivalent circuit when you now look as shown here. So you can see now that these two, this was our X, this was our Y, they're in series, but in parallel with the 21 there. So in the end, you have a scenario like this, 7.292 in series at 10.5, but in parallel with 21 to arrive at 9.632 ohm. Therefore, you can now calculate the current using Ohm's law, which is given by supply voltage divided by the equivalent resistance, and that's 120 divided by the resistor you've gotten there to arrive at 458 amps. Now, the same circuit can be simplified by taking, for example, from that original circuit, if we chose to not necessarily break this star point there, but we chose to simplify this part, which is connected in delta. So you have point A there, being connected to point C, and from point A being connected to point N. So from A to C, you have 12.5. From A to N, you have 10. Then from C to N, there's a delta there, and you have 5 ohm. So you can break this by converting it to the star. And then get maybe the middle point there, let's call it capital N. So you can calculate RAN, which is opposite resistor, 12.5, multiplied by 10, divided by the sum of 10 plus 5 plus 12.5, which gives you 15 plus 10, 25, 27.5. So we can simplify that to get that first star result there. The second star result there, let's call it RCN. So RCN here, again, opposite resistors, 12.5 times 5 divided by the sum, which is 27.5. Then finally, you can calculate from resistor R small n capital N as 5 times 10 divided by 27, which is the sum of it. So when you do this, you are going to get the following values as shown in this diagram. So you'll have reduced that delta circuit to the star equivalent of this, and another one, that resistor, that resistor. Now, when you look at this, it is now easy to simplify because these here are in series, you can add them together. These two are in series, you can add them together. The answers after getting the two pairs, adding the two pairs on each branch here, you can then treat them as being in parallel, which is what we had here. So you have 15 plus 2.27 in parallel with 1.81 plus 20. Then you get the equivalent. That equivalent added to the 4.58 ohm, 4.54 ohm. Then once you add it, you're going to end up with one resistor, which will be in parallel with the 30 here. Okay. And then now it's easy because to be that 30 in parallel with that. And this, I have shown it in the next slide. You can see here, after simplifying, you end up with the 9.642 in parallel with the 30, and you still get the 9.632 ohm, which was the original resistor we had gotten even in the first one where we had done the star to delta transformation. So you still end up getting the same values of current. So it doesn't matter which part you break, or you can choose to break the star point or transform it into delta, or you can transform the delta part into star. And once you do that, you find that now the circuit is easy to simplify. Okay, so if you have understood this, I want you to go and try this tutorial. I've given you the the questions and the solution, the equivalent resistor answers are given below. Try this one and also try the one on this slide. I'll be also interested if you can try this one as well. Otherwise, this marks the end of our lecture presentation. Thank you for listening.